Hello and welcome to today's webinar. I'm just excited that everyone here is learning about the torque sensors and how to best choose the one for your application. So just some housekeeping. As the graphic there said, their mics will be muted for today's presentation. However, that doesn't mean that you can't participate in the conversation. Feel free to use the chat feature to ask any questions that you might have or to make any comments. Casey is manning the comments and questions, and we'll have a time at the end of the presentation to go over those in a little Q&A time. So first of all, thanks so much for being here, taking time out of your day to join us. I hope that you learn which sensor is going to be right for your specific tool. And also how the sensors actually work. There's a couple different sensors, different styles, and we'll talk about how those work. So my name is David Cash. I'm a member of the marketing team here at Mountz. I've been in the torque tool industry for over 20 years now, and I've been with Mountz for over 15 years as well. So speaking of Mountz, if you don't know much about our company, it was founded in 1965. We moved to Silicon Valley in San Jose, our current corporate and West Coast service center. We were the first company to develop a torque analyzer for the military. We also have our warehouse, distribution, and Eastern Service Center located in beautiful Foley, Alabama. As well. So that's a little bit about me, a little bit about Mountz. So let's go ahead and jump into today's topic. How to select the right torque sensor for your application. So we're going to go ahead and get into that. First, we'll just talk about the obviously the risks that are involved with not having good torque control. A 3-cent fastener could simply fail if it's not torqued properly and cause a catastrophic damage. So we want to make sure that the torques that are being called out for are being achieved. And we can do that through the use of torque sensors. So we don't want situations where we have an under torque problem or we have an over torque problem, but we want it just right. So those are some of the obvious risks that are involved with the torque control. And so how can torque sensors help with that? So first, what some of the values that come with measuring our torque values. So first, it gives us the opportunity to evaluate our tools to make sure that they are performing the way that they're supposed to, that they're meeting the specification that they're meant to meet. We can also take a look at traceability. The analyzers and the sensors are traceable to a standard. Once those tools are then calibrated or tested using that sensor, that traceability is now moved to those specific tools. So we can evaluate how the tools perform. We can evaluate the traceability, and then we also have the documentation that goes along with that. So the value of having measuring equipment is great. So when we look at measuring torque, the question often is, when do I measure my torque? And there are basically 3 different times that we can use measuring torque. And that would be, first would be prior to assembly. The second would be during the assembly process. And then third, after the assembly process. So obviously prior to that, we're using it to calibrate our tools. We're also validating to make sure that the tools are performing the way that they are supposed to. During the application, we have the ability to monitor how the tools are performing using our measuring devices. And then we also have after the fact doing auditing and using sensors to be able to do the audits for the assembly after the fact. So those are the different measuring times that we can use the certain devices. And so when we look at our poll question for today, we're looking at in your process, which area or which time are you doing your torque calibration or your measurement checks? Is it before? Is it during? Is it after? Is it all of the above, or is it none at all? So we'll go ahead and we'll let the respondents fill out the poll question, and we'll see what kind of answers we get here coming up. So all right, we'll give just a few more seconds here. All right, the majority of the respondents came back with all of the above. And so that is really good. So with that advice, we should be able to help guide you in the right direction for the certain types of sensors that you may be needing to use for all three of those areas. So when we talk about torque sensors, what are they? Well, they're really torque transducers, and we can use them they're primarily giving us the data through the measurement of resistance. And we'll talk a little bit more about that in the closer to the end of the presentation, but it basically gives us the ability to take an analog signal, converts it to a digital form that is extremely accurate, and then gives us to us in our through our torque analyzer. So the package, I guess the way that it comes, we have our torque sensor, and then that sensor is then married or paired to a torque analyzer. So some torque sensors are built into an analyzer. Some sensors we can plug into maybe a handheld device, and you'll see some of that that I have here today. But when you look at the sensor itself, the accuracy of that that you may see on our website with our sensors, you will see a plus or minus 0.25% of full scale. Now that is not really great when you're talking about being able to measure throughout the full scale of the analyzer, or excuse me, of the sensor. But when that sensor is then paired with an analyzer, that accuracy statement changes to plus or minus 0.5% of reading. So, and the calibration that is done with the analyzer and the sensor, that's under the Z540.1 and the ISO 17025 standards. So there's a big difference between a reading, an accuracy statement that's of reading, and an accuracy statement that's of full scale. So full scale would mean you take the largest value of the sensor, and then you use the plus or minus, and that's going to give you that variant throughout the entire range of the sensor. Now, if it's of reading, that's different. So you're taking the plus or minus from the actual reading, and you're using that at 0.5% for 20 to 100% of the scale. So you get a much better accuracy statement when the sensors are paired to an analyzer. So wanted to demonstrate that. So there's a couple of different styles of a torque measurement. So we have our static sensor versus our dynamic measurement. And so the static measures at one specific time. The dynamic measurement will continue to be giving readings as a fluid type of output. So those are the basic two different types of measurements when it comes to torque sensors. And then the sensors themselves. So we have a couple different styles of the sensors. The first would be the torque reaction sensors. And these types of sensors are used to calibrate tools. They could be either hand tools, torque screwdrivers, torque wrenches. There also can be power tools. You could be using for clutch tools, for DC type tools. You can also use them for pulse tools. You for sure do not want to use them with impact tools. The reaction sensor is going to allow us to do the calibration. And so if we look at what those different types of torque reaction sensors are, let's go ahead and take a look real quick. So our first sensor is going to be the MTX sensor. And this is used for calibrating tools that are extremely low in inch ounces. So this particular sensor measures starting at 1 inch ounce and can go up to 160 inch ounces with different models within that specific range. We also have our BMX sensors, which are some of the examples I have here is this sensor goes from 5 to 50 inch-pounds. This sensor here goes from 5 to 50 foot-pounds. And then I have another sensor here that goes from 25 to 250 foot-pounds. And we can go all the way up to 5,000 foot-pounds with our different BMX torque reaction transducers. So these sensors also start at a lower value. We can go to 2 inch ounces with that all the way up to 5,000 foot-pounds. So currently right now I have this sensor paired to this torque analyzer, our LTT product. Unfortunately, you can't see the screen, but that's okay. I don't have the analyzer itself bolted down, but I can show you just basically how we would use this to calibrate our tools for like a torque screwdriver here. So in this case, I can take the drive, square drive, and go straight into the analyzer. If I go ahead and then I cam over the wrench, we're going to see our reading on the torque analyzer. And we can make adjustments to the tool and make sure that it's within our specifications. So that can be done with hand tools directly straight into the analyzer itself. We can also use torque wrenches as well. So if we have like our FGC cam over screwdriver, you can use this in the drive. We would then take our readings, and then that was going to give us our torque value output that we can test for our torque wrenches. It can also be used for click wrenches as well. Now, if we want to use this style of analyzer for a dynamic tool, such as a electric clutch screwdriver, we can do that as well. We do need to add a rundown adapter to the sensor. And basically the rundown adapter allows the tool to get to its operating RPM speed. We have a series of washers inside the rundown adapter that will compress and to basically allow us to simulate what the joint characteristics might be for a specific rundown. So if I have, for example, I have electric clutch shutoff tool, and we can test that here. We just simply go into the drive on the rundown adapter. We go ahead and run that down. The tool will shut off. We then get our torque reading. And then we can make adjustments accordingly to the tool. If we need to increase the torque or decrease the torque, we can do that, and then go ahead and take our readings again to verify and make sure that we are within the specification. So the rundown adapters we can use in not only the inch pound, but we can go up to larger ones with our 50F, and then we do have larger rundown adapters as well. So that is the reaction transducers. This gives us the ability to calibrate and verify and check the output that our tools are producing. So next is going to be our rotary torque sensors. And the rotary sensor is a fantastic tool because it allows us to actually see the torque values that we're getting on our actual part. So the rotary sensor goes in between the tool output and our bit, and then that can be placed onto our application. We can run the tool and it's going to give us the torque value that we're given on our application. And so this is real important because you just saw on our testing of our reaction transducers when we're setting up our tools, we want to make sure that that correlation between the joint simulator that we're using and our actual part, that those values are consistent. And if there is by chance a irregularity in the joint that we are seeing, we can use the rotary transducer to see what we're getting on our part, and then we can make adjustments to that. The rotary sensor itself can also be used as an R&D device. So if you are looking to develop a torque specification, you can use the rotary sensor to see where at which point your fastener is going to yield and fail, and then you can back off that torque value, usually 20 to 25% or so, and that's going to give you a good starting point to give you the torque value, because oftentimes a engineering document may actually look at the torque values for a particular fastener, and they may have gotten that value just off of a guide or a recommendation for that particular fastener, but it may not necessarily work for the materials that are being used. So if there are some irregularities that are happening within your assembly process and you want to see how your tool is performing on your application, we can use the rotary torque sensor to do that. Now, there are a couple different styles of the rotary torque sensor. So we do have the rotary sensor. We also have a rotary sensor that will also give us an angle. So in every circle, we have 360 degrees of rotation. So that is going to give us a reading at every angle point that we can see. And in our analyzer software, you can set that up to be able to look at a specific angle value. If you want to do a torque plus angle, you could use the rotary sensor for that as well. Now, if we want to be able to constantly be monitoring our torque output during our assembly process, we can certainly use a rotary transducer to do that as well. But we would want to use a brushless rotary sensor. That's going to allow us to have a maintenance-free process where there's no contact on the moving pieces. That's all done through magnetics. And we also have that same brushless style available in an angle transducer as well. So you have that ability to monitor continuously your application if you so desire to do that. So if we take a look at the different rotary styles that we have here, if we're back to our bench here, let me just move some of these. And so we have now one of the features that we do have with our rotary sensor is the ability to store our calibration data actually in the sensor. So you may have seen on the display, let me just move this over so we can see this correctly. All right, so the calibration data is stored within the sensor itself. So this gives us the ability to monitor to make sure that our sensors are staying within the calibrated range of the date intervals. We recommend primarily that you have your sensors and analyzers calibrated either on a 6-month or a 12-month interval to make sure that you're following within the guidelines of your torque program. So the rotary style transducer, we do have that ability to be able to test. Again, this can be used with a power tool. This also can be used with a hand tool. And it can also be used with a static tool as well. So if we want to see what our value that we are getting, so we can go ahead and we can get our values from our screwdriver, and it's going to be a little bit different than what we may see on our analyzer because of the different joint characteristics that are happening. If we wanted to use our power tool for this, we could certainly do that as well. So I'll go ahead and we pull the fastener up, and then we'll go ahead and run it down. And now we get our torque value. So we're actually being able to test our tool on our application with the use of the rotary transducer. And again, this can be helpful for being able to determine a torque value to make sure that the joint characteristics are aligned with your joint simulators. And if you also wanted to be constantly monitoring your output for your application. So this would be an example of the sensor that would be used with our brushless sensor. So again, this is a maintenance-free item. Our regular RTSX product does have brushes on them. So, and we'll show you how that works coming up here. And that's the rotary transducer. Oops, wrong button. All right, and so then our last torque transducer that we have is going to be our torque screwdriver analyzer, sensor. So with this screwdriver, you can use this again as an R&D device. You can look at managing your application to see where a part may fail. If you are seeing some issues with a specific application, you can also use this to do joint auditing or fastener auditing after a particular fastener has been torqued. You could do a breakaway test. You could also do a first movement test with this. And so the torque screwdriver has the sensor built into it. And so let's go ahead and take a look at what that sensor looks like. And so again, this particular screwdriver has a specific range to it. This one goes from 1 to 10 inch-pounds. We have a 5 to 50 inch-pound transducer as well for the screwdriver. The end of it is static, so this is almost just like a traditional screwdriver. It's not going to cam over, and it's not going to do any type of release or breakaway. So if we want to be able to see what we're getting on a specific part or application, we can simply go ahead and we can take this fastener and we run it down, and then we can go ahead and see where this might fail. If we wanted to do, again, some auditing, we can mark a line on the fastener and then also on the substrate. We can then break that fastener away and then bring it back, those two lines together, to see what our values are getting for that particular joint, so that you could do that testing after the fact. So this would be how we can use the torque screwdriver sensor in conjunction with our analyzer and our application. So when we take a look at the sensors themselves, how do these sensors work? So how do we take a analog signal, we convert it to digital, and we get our torque output? So we talked about the resistance and or measuring resistance, and that's done basically through a strain gauge that is on an element within the transducer. So the strain gauge is basically an electrified circuit. It's a very small, very thin laminated material, and it has the circuit componentry within that lamination. So as the strain gauge is laminated to our substrate, it could be glued, it could be, in this case, or in other cases where those gauges are used, they could be welded, things like that. Once that is fixed to its substrate, then any type of torsional change or flex within the strain gauge is going to produce the ability for us to measure a voltage change due to resistance. And if we use the Wheatstone bridge, basically what that does is it allows us to be able to take the voltage, and we can see what the resistance is from that, and then with that we then can correlate that to the flex or the torsion within the link or element that's being tested. And so as the twisting force again, or the movement of the element, we do see a change in resistance, which is a change in our voltage, which then allows us to be able to convert that to our torque signal. And that signal is amplified, and we can get very specific with slight changes within the structure of the link. So what that looks like if we were to go ahead and use this in a graphical type of application. So this is our link or our substrate that is within the torque sensor. And as we apply our forces to the torque, we get a torsional change within the element. And you can see that the strain gauge is also flexing and moving, and that's how we can measure the resistance that we see within our readings. So the strain gauge is electrified. There are leads and electrical components coming off of that that will supply the voltage, and then we can then read what the resistance change in that particular gauge is. So how does this work when we're looking at the rotary style transducer? It's a little bit different in the fact that we use slip rings to be able to accomplish the same type of resistance readings. So as the shaft of the rotary sensor is turning, we are seeing resistance, and then when it finally torques, we do get that torsional change in the cylinder in this case, and then that gives us our torque value that we would be using or reading from the rotary sensor. That would be an example of the brushed sensor. The brushless sensor for the rotaries, again, there's no contact with that, but it is done through electromagnetics. So when we take a look at the particular applications for a review of the different sensors that we can use, if we want to use the sensors for calibration, we could use our MDX and our BMX or reaction style transducers. If we want to do any type of joint analysis, we could use our rotary sensors, which would be our RTSX. We have an RTSX-A as well, the brushless and the brushless angle, and then also the SDX screwdriver transducer as well. If we wanted to continually monitor our application, we're constantly getting our torque values, we would want to use the rotary brushless sensors. If we wanted to do any type of torque verification, we could use all of the sensors that we have. Primarily, you would probably use the BMX and the MDX as the first line for the torque verification. If you wanted to do any type of tool validation or a gauge R&R study, you would want to use the BMX and the MDX sensors. If you wanted to use some process capability studies in relation to how the tool is performing on your application and the results that you would getting, you would want to be using the rotary style transducer. And then finally, if you wanted to do auditing of any type of fastening, then you'd want to use the brushless angle, or you could also use the rotary RTSX angle. And you can also use the SDX in some situations. Now, each sensor, as I mentioned, does have a specific range that it deals with. So you usually have basically 10% of the final or the maximum output. And you can see that with the ability of our gauge, that small little package, if we add too much torque to our sensor, we're going to damage that, strain gauge. And now our sensor is going to not give us the correct values. And so you would see that in your analyzer as a negative type of offset. So when you try to zero your analyzer, it's not going to zero, but you would have some type of offset value. That is indication that the electrical component of the strain gauge has been deformed beyond its ability to measure the resistance correctly. So with that, that is going to bring up our question and answer section. Let me grab a drink of water. And Casey, if you have any questions, feel free to ask away. I think you are muted, Casey.
Yep, I'm sorry about that. I have one question in the chat box here, and it is the connection between the transducer and the display analog or digital?
That's going to be a digital process.
that is the only question we have right now in the chat. If you guys have any other questions, feel free to enter them in the next couple seconds, and I'd be happy to pass those along to Dave. We will also be sending you a follow-up email, so if you want to ask those questions in email format, we can take those for you there as well.
All right, if there aren't any other questions, then again, thank you so much for your time. I hope you learned how the sensor works, how you can use it in your applications, and how you can better your process. Thanks so much, and have a great day.